Hey guys, so today we're going to work through the Test 5 review. This is available for you to download, or you should have been able to pick it up in class. So problem number 1, there's going to be a couple different versions of it. It says to graph the following exponential and logarithmic functions on the given coordinate systems and fill in the given t-charts. Remember to graph exponential and logarithmic functions. These are what I call plug and chug problems. That's where you pick the values for your x, and then you will have to chug or compute out your values for your y's. So I usually do -2, -1, 0, 1, 2, and then I gave you an extra row, so I'm going to do 3. So the first problem says f of x equals 4 to the x. So 4 to the -2, remember that's 4 to the -2 power. Negative exponents means you flip. If you have a whole number, it becomes a fraction. So that means my f of x is going to be 1/16. Same thing, similar process for -1. 4 to the -1 would be 1/4 to the first, which is, 1/4. 4 to the 0th power, well, anything to the 0th power is 1. 4 to the first power, 4. 4 squared, 16. And 4 to the third is 64. So now we're going to plot these points. So at -1, we were at +1/4. 0, we were at 1. At 1, we were at 4. You don't have to use every point that you have on your chart, but you do need to graph it with a couple of points, and you do need to show that it hugs the horizontal asymptote, that you are not going to cross that horizontal asymptote there at the x-axis. So those are the important things when it comes to graphing these. Okay, so for B, we have f of x equals 3/2 raised to the x power. So, again, I'm going to do the exact same process. -2, -1, 0, 1, 2, 3. So in this case, 3/2 raised to the -2, excuse me. Remember, what that did up here was we went from a whole number to a fraction. If we're already a fraction, then we just simply flip. So then it becomes 2/3 to the 2nd power, which is going to give us, goodness, my lead is not good, 4/9. Do the exact same process for -1. That'll give you a 2/3. 3/2 to the 0th power is 1. 3/2 to the first power is 3/2. 3/2 squared is 9/4. And 3/2 to the third is 27/8. Okay, so I know at 0, I'm at 1. At -1, I'm at 2/3. At -2, I'm at 4/9, which is just over half. At 1, I'm at 1.5. At 2, I'm at 2.25. So notice it's a little bit more like stretched out in this case. Again, the important part is that you use a couple of the points that you have. You draw it to where it's going to hug that asymptote, not where it's going to cross. And then one more thing that I want to point out with problems like these is that if you have, like, up here, let's see, we'll look at the 4. If I were to have -4 to the x, this is different than -4 to the x. So make sure that you realize that, because what this top one, this -4 to the x means, it means -1 times 4 to the x. Whereas down here, I'm taking -4 times itself however many times x is. So like if x equals 2, let's say, then this top one would be -1 times 4 squared, which is -16. Whereas this bottom example where you have the parentheses is -4 squared, which is -4 times -4, which is +16. So you do need to be careful with those, or you will get them wrong. Okay, so let's flip over to the back of the first page. So C says f of x equals 3 to the x, and g of x equals log base 3 of x. So obviously we have two different t-charts that we have to fill out because we have two different equations that we are going to graph. Always start with your exponential. -2, -1, 0, 1, 2, 3. So 3 to the -2 is going to become 1/9, 1/3, 1, 3, 9, and 27. So I'm going to go ahead and graph my f of x since I have my t-chart done, and then we'll talk about how to do the t-chart for log base 3 of x. So at -2, I'm at a 9th, I'm at a 3rd, I'm at 1, and 1, 2, 3. Obviously, I don't want to do a 9th or a 27, so I will just draw those. So there's your f of x, there's your exponential. Now, hopefully you remember that if you have an exponential with the same base as a log, then what you do is you flip-flop your x's and your y's. So that means my f of x becomes my becomes my x for my g of x, and my x becomes my g of x. So that means my x is 1/9, 1/3, 1, 3, 9, and 27. So then my g of x is -2, -1, 0, 1, 2, 3. So now I can graph these, and I didn't really have to compute anything because all I do is I flip-flop my x's and my y's. So when x is 1, my y, or my g of x, is 0. When x was a 3rd, I'm down at -1. When x is 3, 1, 2, 3, I'm at 1. And that's really all I need to graph this. So again, use about 3 of your points to graph. The important part when you're graphing your logarithms is that you hug your vertical asymptote. Logarithms have vertical asymptotes at the y-axis, whereas exponentials have a horizontal axis at the x-axis. So when you graph these, it's important to note those. You don't have to draw in those asymptotes as long as you draw your graphs so that it shows that your graphs are hugging at those points. Okay? All right, let's move on. Number 2 says use compound interest formulas to solve the following problems. So for this, you do have to memorize your compound interest formulas. Compound interest formulas are the A equals P times 1 plus R over N raised to the NT, and A equals P E-R-T, or PERT, as I call it. And remember that E is the number E. That's not another variable. The rest of this means that your P is your principal, your R is your rate, your T is your time in years, and the N in this first one tells you how many times you compound it in a year. And this bottom equation is your compounding continuously. So you do need to memorize those for the exam so that you're able to use them on this problem. It says round to the nearest cent, so it means you're going to have 2 decimal places. And obviously, if it rounds to the nearest cent and you're using an equation like this, you need to have a calculator. You will not be allowed to use your cell phone on the exam, so you do want to make sure you have a calculator to use. It says find the accumulated value of an investment of $10,000 for 5 years at an interest rate of 5.5% if the money is compounded semi-annually, compounded quarterly, compounded monthly, and compounded continuously. So in our problem, it says we have an investment of $10,000. That's our principal. It says for 5 years, that's our time. And it tells us our interest rate is 5.5%. Well, there's your rate. It even tells you rate right there. And then what changes is how often you compound that. So if you compound it semi-annually, that means your N is going to be 2. Semi means 2. So 2 times a year, you're going to compound this money. So I'm going to write out my equation. which is this top one. A equals P, well that's 10,000, principal is 10,000, times 1 plus our rate. Now you do have to convert your rate from a percentage to a decimal, so that becomes 0.055 all over your n. Well, if it's compounded semi-annually, your n is going to be 2. All of that is raised to your n times your t, so 2 times 5. If I type all of this into my calculator, which you can do with a pretty basic scientific calculator, what you're going to find is that it is $13,116.51. Okay, so now let's do quarterly. If we compound quarterly, then our n is going to be 4, because there's 4 quarters in a year. So that means we're going to do this exact same equation, but instead of writing 2, we're going to have 4. And yes, I'm going to write this equation every single time that I use it. And the reason for that is because it's going to help it to stick in my brain what this equation is, so that I can remember it for the exam and for the final. So I wrote the equation, but instead of my n being 2, my n is now 4. And if I type that in, I find $13,140.67. So notice it went up by about $24 by compounding it quarterly. If I compound it monthly, there's 12 months in a year, so that means my n is 12. My principal is still 10,000, 1 plus my rate. Now my n is 12, all of that raised to 12 times 5. I type that in and I get $13,157.04. So notice it went up again. The last one says I compound it continuously. So if I compound it continuously, then I'm not actually having an n because it's just constantly compounding. So that's when I'm going to use this other equation for PERT, because I'm going to use e to compound. So that means we have a equals, well, it's my principal, which is 10,000, times e to the r, which is your rate, 0.055, times t, which is 5. Again, a scientific calculator, you can type that in, and you're going to get $13,165.31. So notice that it kept going up because we kept compounding it more times in a year, which means that our money was growing more times. A problem like this is always on the final exam. So it is important that you do know how to work these problems, how to type these into your calculator, and that you do have these formulas memorized so that you have them to use on the final exam. All right, flipping over. Number 3 says to write each of the following expressions in its equivalent exponential form. So we are not solving these at all. All we are doing is we're going from logarithms to exponentials. To do that, we have to use the definition of a logarithm. That's the base becomes the base, your answer becomes the exponent, and what you were taking the log of becomes your new answer. So if I'm looking at A, I have 4 equals log base 2 of 16. So my base is 2, log base 2 of 16. So the base becomes the base of my exponential. The answer of my log becomes my exponent, and then what I was taking the log of would become my new answer. And that's what we're going to do on these next two. So the base becomes the base, so the base of this one is 9. The answer becomes the exponent, and what I was taking the log of becomes my new answer. Last one, we have y equals log base 5 of 125. So the base becomes the base, the answer becomes the exponent, and what I was taking the log of becomes my new answer. That is all you need to do on these problems. We are not going to solve for the different variables. We're not going to do anything else. Number 4 is kind of the opposite of what we just did. So it says write each of the following expressions in its equivalent logarithmic form. So here we went from logs to exponents. Here we're going to go from exponents to logs. So it works very similarly in that we're going to go the base becomes the base and our exponent becomes our answer. And then our answer over here becomes what we're actually taking the log of. So usually when I do these problems, I will go ahead and write log, and then I have the base spot, I have what I'm taking the log of, and I have my answer spot. So I have my 3 spots to fill in as I go. So the base of your exponent becomes the base of your logarithm. Your exponent becomes your answer. And then what your answer was for your exponential becomes what you were taking the log of. Okay, we're going to do that on the next 2 problems. All right, so we have 5 to the negative 3 equals 1 over 125. The base of my exponential becomes the base of my logarithm. The exponent becomes my answer, and my answer becomes what I take the log of. Last one, 8 to the y equals 300. The base of my exponent becomes the base of my logarithm. The exponent becomes my answer, and then my answer became what I took the log of. Okay. This bottom one says evaluate the following expressions without a calculator by converting into the equivalent exponential form and solving for the variable. So these are all logs. So what we have to do is we have to get them into exponentials and then solve them without a calculator. This is one of the few problems where if you do not show me the middle work and you just write an answer, you will not get full credit because you have to convert to exponentials first. So make sure you show me some work. This first one, this A, is also the one where we have a typo. If you download it from the computer, I did correct it. It's supposed to be log base 3 of 27, not 24. So I have fixed that on the digital version. But right here, the printed version, I had a mistake. So we need to convert this into exponential form and then solve. So log base 3 of 27 equals y. The base of my log becomes the base of my exponent. So 3. The answer becomes my exponent. And then what I was taking the log of becomes my new answer. So 3 to what power gives me 27? Well, if you're not sure, you can type in your calculator or work out on the side. 3 to the first is 3, and 3 squared is 9, and then 3 to the third is 27. So that means y is 3. That's how we would compute these without a calculator. I know it says without, and I just said you could use a calculator to say 3 to the each power, but that's you figuring that out. You have to write this step, not just simply do a change of base over here and solve for y, is what that meant. What that means. Let's look at B. We have log base 9 of 1 over 81 equals y. So the base becomes the base, the answer becomes the exponent, and I have 1 over 81. So I need to solve for y. Notice I have a whole number raised to an exponent equals a fraction. Whenever you see that happen, where you go from a whole number to a fraction or a fraction to a whole number, you know that your exponent is going to be negative, because that's the only way to get it to flip in exponentials. So then I need to ask, how do I get 9 to 81? Like 9 to what power is 81? Well, 9 squared is 81, so that means y is going to be a negative 2 in this case. Moving on to the last one, log base y of 7 to the 4th equals 4. So the base becomes the base, your answer becomes your exponent. What you were taking the log of becomes your new answer. So now I have y to the 4th equals 7 to the 4th. So notice the exponents are the same, and the only thing we have left is the bases. And since they're set equal, that tells me that y equals 7. So that's how you do those. Let's flip on over to the next page. All right, number 6. It says, use the properties of logarithms to expand each logarithmic expression as much as possible. Do not evaluate. So we're not going to solve for any of our variables. But one thing we do want to do is we do want to make sure that we still simplify even as we expand these logarithms. So remember, we learned 3 different properties of logarithms. We learned the product rule, which has to do with when we're multiplying. We learned the quotient rule, which has to do with when we're dividing. And we learned the power rule, which has to do with when we have exponents. So notice there's 3 examples, so you get to do one of each of those. So A is log base 5 of 7 times 3. So that's times tells us we're going to use our product rule. To expand using product rule, we have log base 5 of 7, so that's the first term. And then we do an addition, and then log base 5 of our second term. That's how you expand using the product rule. Okay, let's look at B. Log base 4 is 64 over y. So this is a division problem, so that means we're going to use our quotient rule. Our quotient rule says log base 4 of 64 minus log base 4 of y. Now you may be asking, well, why did you put it over here and not on the answer line? Well, I noticed that I have a base of 4 and I have a log of 64. And I know I can write 4 in terms of 64, like 4 to some power equals 64. Anytime you can do that, it's going to simplify out. Remember, I'll write it up here, log base b of b. When you have the base, it's the same thing as what you're taking the log of. That simplifies out to 1. So anytime that I can write log base b of b in my expansions or in my condensments, I'm going to get 1, which simplifies down. So in this case, I have log base 4 of 4 to some power, so I'm just putting a line there right now, minus log base 4 of y. Well, 4 to what power is going to give me 64? Well, if you weren't totally sure, we did already compute this on the very front page. Whenever we did our t-charts for number 1, this was 4 to the x power. 4 to the third gave us 64. So that means this is log base 4 of 4 to the third power. Since I have the base is the same as what I'm taking the log of, all of this simplifies to 1. So that's going to leave me with 3 minus log base 4 of y. So even though I'm not evaluating and solving for my y or anything like that, I do want to continue to simplify it as much as I possibly can. So I don't want to leave this as log base 4 of 64. I want to keep simplifying it until I get that 3. Notice on the first example, even though I had the base was a number and what I was taking the log of was a number, I couldn't write 7 with a base of 5 exponentially and then simplify it. Same thing with 3. That's why I couldn't take that any further. But 64 I could write as an exponential with a base of 4 and thus simplify it out. Our last one in this category is log base m, or excuse me, just log of m to the negative 8. So this is our power rule. Power rule says that if it's raised to a power, I can pull that power out front. So this becomes negative 8 log base capital M. Or it's not log base, it's just log of capital M. This would be a common log that has a base of 10. All right, let's look at number 7. Use the properties of logarithms to condense each expression as much as possible. Make sure to simplify where possible. Do not evaluate. So this making sure to simplify where possible is like what we did up here on B. And so anytime you have the base is a number and what you're taking the log of is a number, you're going to want to check to make sure that you can't do this simplification like we did up here. So that's my little word of help. Like make sure this is a number and this is a number. We can't rewrite that with the base. Okay. So again, we learned 3 different rules. We have product, quotient, and power. So we're probably going to use all 3 of those since we have 3 examples to work with. We have ln of x plus ln of 7. This plus tells me that I'm going to use the product rule to condense these. I'm going to combine them together into one log. So instead of ln of x plus ln of 7, I have ln of x times 7, which is just ln of 7x. I brought them together. Here I have log base 3 of 405 minus log base 3 of 5. This minus tells me it's going to be a quotient rule. So I have log base 3 of 405 over 5, which becomes log base 3 of 81. Now at this point, I would ask, can I get 3, can I write 81 as an exponential with 3 as your base? I'm pretty sure I can, and so I'm going to want to do that. Log base 3 of 3 to what power is 81? Well, 3 to the first power is 3. 3 squared is 9. 3 to the third power is 27. And 3 to the fourth power is 81. So log base 3 of 3 to the fourth power is the same thing as log base 3 of 81. But you want to keep going with this because, see, now I have base is the same as what I'm taking the log of. So all of that simplifies to where I'm left with just 4. So you do have to check this. And really, here's the way I would do this. Kind of like I made my little chart over here with my 3 to my different powers. That's what I would do. Anytime that I have the base and I have a log that I'm taking the log of, and they're both numbers, I would run through a couple of different powers to make sure that I either can write it like this, where I had 3 to the fourth, or I couldn't. Like, oh, it was on the other page. Where'd it go? Or no, it's up here. Excuse me. This log base 5 of 7, if I wasn't sure if I could write 7 as a base of 5, I could have said, well, 5 to the first is 5 and 5 squared is 25, and known, okay, well, wait, I've already bigger than 7, so I can't write that with the same base, so I'm good there. And I could do the exact same thing over here with 5 to the base of 3, or log base 5 of 3. I could say, well, 5 to the first is 5. That's already bigger than 3, so I can't write 3 with a base of 5. And so that's how you could kind of eliminate that out. Really, anytime that the base is a number and what you're taking the log of is a number, you need to check to make sure that you can't do any of these simplifications. Okay, last one in this section, we have 7 ln of x minus 3 ln of y. So these coefficients out front should immediately tell you that you're going to use the power rule to pull them back inside as exponents. So that becomes ln of x to the 7th minus ln of y to the 3rd. Notice we still have two different ln's, or two different logs, and we have this minus in here, so we still need to condense them further. The minus tells me it's a quotient rule. So I have ln of x to the 7th all over y to the 3rd. So don't just stop by doing the power rule. Sometimes you're going to have more than one rule in order to totally condense them in. Okay. Number 8, use the change of base procedure to obtain a decimal approximation for the following logarithms. Evaluate to 4 decimal places. So log base 5 of 13. So if you pulled out your calculator right now and I told you to type that in, you wouldn't be able to do that. Why? Because you're going to have a common log button that is just log base 10. It's probably just going to look like a log button with no base, because that's log base 10. That's your common log. Or you're going to have your natural log, which is your log base e. So you're going to have this ln button and you're going to have this log button. But this is log base 5. That's not base 10 or base e. So how do you type that in? Well, that's what the change of base procedure allows you to do. Change of base procedure says that log base 5 of 13 is the same thing as taking log of 13 and dividing that by log of 5. So these are the common logs, and I did what I was taking the log of on top, and I did log of the base on bottom. You can also type that in as ln of 13 over ln of 5. Either one of these is going to give you the same answer. So it doesn't matter if you do common log or the ln, as long as you do 13 over 5. You do what you're taking the log of over the base. If you type that into your calculator, you have 1.59 0.37. I'm going to 4 decimal places. You're going to do that for the next 2 examples. So log base 0.1 of 17 will become log of 17 divided by log of 0.1, which is negative 1.2304. And the last one is log base 14 of 87.5. So I have log of 87.5 over log of 14. Type that in, I get 1.6944. Flipping over. Number 9, solve each of these exponential equations by expressing each side as a power of the same base and then equating the exponents. So each side is going to be a power of the same base. So this one you have to do this way because it tells you to. So what does that mean? Well, 2 to the x equals 64. Notice on my left, I already have an exponential expression. I have 2 to the x. That means on my right-hand side, I need to write 64 as 2 to some power. I need to have the power of the same base, and then I can ignore my bases and just look at my exponents. So this is where you would probably use a calculator and type in 2 to the first power, which is 2, and 2 to the second power is 4, 2 to the third power is 8, and so on and so forth. And what you're going to find is 2 to the sixth power is 64. Now that I have my exponentials with the same base, I just set my exponents equal to each other, and so x equals 6. We're going to do that on the next 2 examples as well. So I have 5 to the x equals 125. So again, my left is already set up as an exponential, so I want to write 125 as 5 to some power. Well, 5 squared is 25. 5 to the third then would be 125. That means my x is 3. Last example, obviously there's a little bit more algebra because my exponent is not just x like it was in my first 2, but it is 2x plus 1. So that means I have 3 to the 2x plus 1 equals, and I need to write 27 as 3 to some power. Well, 3 squared is 9, and 3 to the third power is 27. So again, I ignore my bases, and I just set my exponents equal to each other. So up here, there wasn't anything else to compute once I set my exponents equal to each other. But now I have an algebraic expression, so I still need to solve for my x. I'm going to subtract over my 1, and I get 2x equals 2. If I divide both sides by 2, I find that my x equals 1. Okay. The last set of problems is solving logarithmic equations. So it doesn't tell you how. Most of these other ones kind of told you how to solve these. This one doesn't. And that's because in order to solve logarithmic equations, you use the definition of a logarithm, which is your base becomes a base and your answer becomes the exponent. So you're going to have to convert from logarithms to exponentials and then solve for your variable. Okay, so we have log base 3 of x equals 4. So your base becomes your base, your answer becomes your exponent, and then what you were taking the log of becomes your new answer. So I have 3 to the 4th equals x. So 3 to the 4th means x is 81. B says log base 5 of x minus 7 equals 2. So the base becomes the base, my answer becomes the exponent, and what I was taking the log of becomes my new answer. So 5 squared is 25. I'm going to add that 7 over to where I get x equals 32. This last example, part C, again, if you downloaded the digital version, it will already be corrected, but on mine, it has the plus here for 3x plus 2. I really would prefer that to be a minus. It makes for a nicer answer in the long run. So I switched mine to a minus. Again, yours may already be a minus, and if so, you're good to go. So this is log base 4 of 3x minus 2 equals 3. So the base is 4. The answer is my exponent. and what I was taking the log of becomes my new answer. 4 to the third power, we've done this a few times in this paper, in this review, that's 64. And then I have 3x minus 2. I'm going to add that 2 over, so I have 66 equals 3x. Divide both sides by x, and I find that x is 22. And that is the last problem on the review. Remember, just like with all of my reviews, if it's on the review, it's on the test. If it's not on the test, or not on the review, then it's not on the test. So this is a really good study tool for you to figure out what you need to study, what you need to know for the exam. It will be laid out very similarly. Don't forget, you do need to memorize your equations or your formulas for interest problems. And that is all for Test 5 review.